Last time we divide the two equivalent definitions first. So we have the integral, right? Integral formula. So let's see this integral is quite commonly you can get to this form um, by many physics problems. So dt. There's a there's a restriction on z, so when z is greater than zero, in order that the lower limit is well behaved. But the gamma function is defined for all z actually, except the poles, obviously. And then we showed that last time with some effort, showed that this is equals to the what we call the infinite limit. So this is also equals to last time which limit of n goes to infinity. You have this basically n factorial. It's just writing it explicitly. 1 times 2 times 3 times n. And then divided by, it's hard to write a straight line here. C plus 1, C plus 2, all the way to C plus n. And then there's nz. Okay. And so once you're writing like that, we show that this is the correct limit. And you see that you can actually take away this restriction. So this can be defined for all z except the pole in the, well, the zero in the denominator. So z equals 0 or -1, -2. So it's not defined as for 0, -1, -2, or the negative integer. So you can say that gamma has poles, and you can see that they are all simple pole at 0 and all negative integer. So that is fine. Another thing, you can see that there's no zero. There's no zero. Gamma cannot be zero, and uh, the numerator cannot be zero. So and we'll see another form in a minute that 1 over gamma actually is so-called entire function, is not singular except at infinity, is equals to infinity. So that's one property. Okay, and right, so this is the infinite def. I mean, you can see that some property of the gamma function already in this one. Another property is quite trivial, is that you can evaluate gamma at some particular point, say in particular c equals to 1. Right, c equals 1, you set c equals 1 in here, so obviously f of z becomes 1. So this is you can write it explicitly, so if you cannot see it right away, so this becomes n factorial. So you can say it's n factorial. And this is 1, right? And this is 1 plus n, so this is n plus 1 factorial. And then you add extra n in here, right? It's equal to 1 extra n. So altogether, n plus 1 factorial is just n factorial times n plus 1, so n over n plus 1. Right? So that in the limit of n goes to infinity, it goes to 1, right? So so the special value is like that. So that kind of straightforward. Uh, Another property is the actually is a quite useful or quite commonly used formula for gamma function. You evaluate that using the same formula with z equals to c changes z plus 1. So basically everything move up a little bit. So same limit. So same n factorial in here. and then you have n to the z plus 1, right? And then everything in is z plus 1. So this change to z plus 1, z plus 2. This is z plus 1, n plus 1. So you're missing a z, so you want to add back a z here, and then everything go back to the same, right? Because you're changing z to z plus 1, right? So you have this becomes here. You add a z, add the extra z in both numerator and denominators. This becomes that, and this becomes z plus 2. And then this becomes z plus 3. And altogether, this becomes z plus n plus 1. But before that, you have a z plus n, and then a z plus n plus 1. Right. And and then you take the limit. Then you write this n to the z plus 1 as see, let's erase that. Instead of writing not this one. Writing is n plus z and then an extra n here. Okay. And now you see that except this factor and this factor and this extra factor, the rest is just the old gamma function, right? Just this definition. So compare this with that. So that will give you limit of n goes to infinity. You have n here, you have n, and then extra factor, c plus n plus 1, and then a z here. The rest is a gamma function, just the old one, right? You can see that, right? And so, and then in the limit of n goes to infinity, so whatever c is just finite, whatever finite z. So n, this will always n will always greater than z. So this limit always goes to 1. So that is equals to z times c gamma z. Okay, so that's an iteration of recurrence formula for gamma function. So once you have z, you can get z plus 1. So then you can get z plus 2 and z plus 3. You can keep doing that. Okay, so that is a very useful and very commonly used formula for gamma function. Okay, so once you have that, you combine this with that, obviously. So gamma 1 is 1. So using this formula, gamma 2 will be just using this formula, 1 times gamma 1, which is gamma 1 is just 1. So gamma 2 is also 1. Gamma 3 is 2 times gamma 2 is equals to 2. Gamma 4 is 3. Gamma 3, which is 3 times 2. So you can see the pattern, right? So gamma 1 is like the 0 factorial. And gamma 2 is like 1 factorial. Gamma 3 is like 2 factorial. Gamma 4 is 3 factorial. So altogether, that implies the next property. So all the integer, gamma n plus 1 is just the usual n factorial. Okay, so that useful. And some people, because of that, some people use the factorial notation as the notation for gamma function. So instead of writing an integer factorial, we can write any real number factorial or even complex number factorial. Just use that to indicate that it's a gamma function plus 1, right? And uh, that that depends on people's choice. That's one notation is like that, but most people like to write explicit like a function, a gamma function like that. Okay, so but that is coming from this formula, this gamma c plus 1 formula. Okay, and there's another formula, is less commonly used, but we can also derive that because last time using the integral formula, uh, first first is this one, but then we make the change of variable becomes t squared, and then that becomes like a Gaussian integral, and choosing especially choosing c is 1/2 because that's become t squared 1/2 times 2 minus 1 is 0, so you get rid of that term. Becomes a Gaussian integral, and we show that that is the square root of pi. Okay, and now we can do the same thing. Now that's slightly more complicated, so we see if we can figure that out because we can we can do the same thing. So gamma 1/2 and then gamma 3/2 will be like gamma is 1 times, right? Or you can say 1/2 times gamma 1/2, right? So because of this formula, so 1/2 plus 1 is 3/2. So this is 1/2 square root of pi, and you can keep doing that. So gamma 5/2, all the half integer is 3/2 gamma 3/2 would be 3 times 1, 2 times 2, and square root of pi. And do one more, see if we can find the pattern. And 7/2 times 5/2 gamma 5/2 goes to, so multiply another 5/2. 5 times 3 times 1, 2 times 2 times 2, square root of pi. Okay. Now we see if we can generalize that. So gamma, and this is half integer. We can say this is n plus, to get this to half integer is n plus 1/2, right? In any integer, right? And now see how many it is. If so, this the original one, but if 3/2 is this n equals to 1, you get just 1/2. 5/2 is n equals to 2, right? Compare this with the n equals 2, you get two terms, 3 times 1. So and n equals to 3 is 7/2 is n equals 3. You got 3 terms, right? So the number of terms is equals to n, and so you have and then the largest odd integer is just uh, whatever that is. Uh, so this is 2n plus 1, right? Then this is 2n minus 1. So it's 2n minus 1 times all the way times to 3 times 1, right? And then the number of terms equals to this n. So you have 2 to the n power, and then square pi, right? And so this is 1 because 2n minus 1 is 1. Well, for n equals to 1. For n equals to 2, 2n minus 1 is 3. So there's n factor in the numerator and n factor of 2 in the denominator. Okay, and so that's the formula, and some people like to write this as a double factorial. this become 2 to n square root of pi. Okay, okay. Now for all in the odd integer, you have this one, so compare with this one. So integer, you get factorial. Odd integer, you get this double factorial and divided by this power of n. See if I got it correctly. There's a formula later in this section. This is, let me look that up first. This is 13.28. Let's see. 13.28. So we divide that first. Your textbook, the order discussion are a little bit different, but while we are discussing it, we'll divide this one. This one is also quite commonly used. I mean, not elementary application for our level. Sometimes you use that. In different context, you see this thing coming up. Okay, so that kind of a useful formula, right? And so those are the special values of gamma function. Okay, and now we go to, I think we had finished all the discussion with the infinite limit, but from the infinite limit, you can derive another formula, another definition of gamma function, just convert that this infinite limit to an infinite product. So this one is not an infinite product because I mean there's a product, so like n factorial. The n factorial you can convert that to infinite products. The denominator is also, you can also convert that to infinite product. But because there's an explicit n here, n to the z, so you for this factor you need to do some work to convert that to infinite product. So that's what we'll do to divide the next formula, so that the whole thing is infinite product. So and the idea is to first write that just like what we did. There's not enough space in here. So but anyway, maybe just keep writing. So using the infinite product definition, so yeah, we'll see as so maybe just copy it one more time because it's hard to go up and down. So you have all these like product integer factorial, and then you have z plus 1 all the way to z plus n, and then n to the z. And other than the last one, you can write it as an infinite product, and there's n factor in the numerator, but then there's n plus 1 factor in the denominator because this is z plus 1, this is z plus n. So there's n factor here plus a factor of z. So you can take away the 1 over z out, and then keeping the limit because we are not getting rid of all the n factor yet. So and then write the rest as infinite product. So this is using a textbook notation, m as 1 to n, and then just divide one to the other. So in fact, we're writing it as inverse product. So because basically z plus 1 divided by 1 and z plus 2 divided by 2, and so all those is just if you write like so the first one is 1 for m equals 1, it's just 1 plus z over 1, which is just m, right? And then the next one is z plus 2, and then divided by 2. and the 2 plus divided by 2 is 1, and then the factor is c plus c divided by 2. So altogether is c plus c divided by 2, because we are writing as infinite product, so we don't need to keep writing it. Always getting it wrong. Okay, so this include all the factor. M equals 2 is c plus 2 divided by 2. M equals 3 is c plus 3 divided by c. So this product is including all this division. Well, this is in the denominator, so we need to add -1. Okay, and then we need to keep this n to the z. But this n to the z is obviously, we need to find some way to make it like a product, right? And what we'll do is to write n as n to the z. We also like to put it in the denominator, so it's 1 over n to the minus z. N to the minus z is e to the minus log n. And to the z power, or writing this minus log n times z. Right. Okay, so this is, you can see that, right? So you put the negative sign in changing the log becomes 1 over log, right? Log 1 over n, right? Log over e to the log 1 over n is just n minus 1. N minus 1 to the z power is n minus z. And this is in the denominator, so it is nz becomes n to the minus z in the denominator. Okay, so that is something. At least we are making some progress. The next thing is because this is in the denominator, all these are in the denominator, this is in the denominator, we can more easily just define just invert the formulas 1 over gamma z, and becomes z, as this becomes in the numerator, and limit of n goes to infinity. Now that is in the numerator again, so minus log n times z, and now all the product 1 to n 1 by z over n. And the reason is that when n goes to infinity, all these you can just change this to n to infinity here, so that becomes an infinite product, but not exactly this one first. I mean, n you cannot just write log infinity here, because not infinity is not well defined. It's actually divergent, so that becomes a problem, a side problem. And what we want to do is to remove the explicit mention in here, and then get to another, either a sum or a product, so to n power or n factor or n terms, so that we just change the limit to n and the mention of n to infinity. And to get rid of this log n, we are using this one result in when we talk in chapter 1, there's when I talk about infinite series, there's one result which is the sum over m. This is um 1 over m to the infinity. And actually, it's just not infinity yet to n terms. And 1 over m. This is so-called harmonic series, right? So this And then, and if you let n goes to infinity, this series diverge. We probably mentioned that. And then, but then if you subtract log n, that becomes a convergent. There's a discussion in chapter one that this limit exists. We take limit of n goes to infinity. This difference is a finite number and is defined as gamma. Okay, then and this gamma is the name of this is where is the textbook talk about that? Mm, yeah, at the first is Euler Maccheroni constant. Many people just call it the Euler constant. Yes, the value need to be calculated numerically, but it's by this definition, and uh, but it's this becomes convergent. This limit exists, and this gamma is an integer 0.577 something. So as it's just a universal number, just like pi or e, but it's less well known than the other two. But it's still a fairly commonly used fundamental constant, the Euler constant. Okay, so in this case, we can use this log this result, so and convert that. So minus limit of n minus log n is like so. So we are using this result. This is a fundamental result, just a mathematical fact. Okay, and substitute this log minus log n to here. So 1 over gamma becomes g, and just take this, substitute this, so it becomes, well, we already have a c here. E, and this one becomes some, just move everything to the other side, becomes, there's a c first, right? There's a factor of c, and there's a minus log n. Minus log n is in here, so there's move, just write a gamma minus sum over m from 1 to n. Now you can explicitly change n goes to infinity and get rid of the limit sign. M from 1 to infinity, 1 over m. Okay, so that's this one. And then the infinite limit becomes m from 1 to n infinity, 1 plus c over m. Okay, and now we can finally use the idea or the mathematical factor e to the sum of the term equals the product of the e to each terms, right? Just use the e to the a plus b equals ea eb, right? Just use this fact and change this sum to infinite product and combine with this infinite product. Okay, that becomes a z e. The first term is just gamma z, and the rest are all the infinite product. We have this term 1 plus z over m, and then this is exponential. There's a minus sign, minus z over m. Okay, so this is 1 over gamma z. Oopsie. Okay. Get, get rid of this m. Okay, so this is equation 13.15. Okay, so this is a form. The text will use n, but this is dummy. It doesn't matter. Okay, so that's the another formula. So now explicitly it's an infinite product. You get rid of the limit signs. It's not taking a limit, although the limit is in the upper limit of the infinite product. Okay, now from this formula, you can see that again. You can another way to see it is this function is there's no explicit singularity here, and other than z goes to infinity. So all this product that you cannot get this to all this product to infinity. This is just power of z, right? And also this is just exponential function. It doesn't blow up other than z goes to infinity. So there's no pole. This function has no pole for the entire complex z pairing except infinity. But that's called an entire function, right? So that is the fact is due to the fact that gamma has no zero. Gamma z has no zero over the complex plane. It's at the pole at the zero and negative integer, but no zero. So 1 over z has no pole. Okay, so that's another property of the gamma function. All right, and so compare with the original limit. So original limit, we write it like that. So this one and that one, and the usefulness is complementary. Sometimes the first one is easier to use. Sometimes the second one, the infinite product, is easier to use. And in particular, in the discussion on the next section, basically the derivative of gamma function, what we call the digamma and polygamma function. Basically, we'll take the derivative of that. Obviously, the derivative of that would be very complicated if you have an infinite product. So what we will do is take the log first, take the log of this function, either this function or the original Euler one. Take the log, because all this product becomes a summation of individual term, because individual log of individual term, and that make it easier. Okay, so that's the convenience for deriving derivatives. Okay, then I think we have done with this infinite